In today's lecture, I will start a new module, which is power distribution system planning. Okay. And today, this is part 1 of this module. It is a very short module, it is a very short lecture. Although this module is very vast or very big, but in this particular lecture, I will basically focus on these economic aspects of power distribution system. Okay. And in this economic aspect, I will basically discuss the some of the parameters, some of the economic parameter which we normally use in power system planning or power distribution system planning. So, in order to understand the power distribution system planning models, which I am going to discuss from next lecture onward, one needs to have an understanding of some of the financial parameters. Okay. Although they are not related to our electrical engineering, but these are required to understand this power distribution system planning models. Okay. So, some of the important financial parameters I am going to discuss in today's lecture. Okay. So, let us start. So, basically in my next lecture onward, you will see that power distribution system planning is essentially an optimization problem, in which we will optimize certain objectives. Okay. And one of the main objectives is to minimize the cost of whatever is associated in planning of a distribution network. For example, if I wish to construct a new distribution network, I need to plan that network, and this planning process is essentially an optimization process, because whatever we will be planning, that planning should be economically feasible. Otherwise, nobody will accept the planning, okay, and nobody will invest, nobody will wish to invest money in that particular planning. So, in order to make one planning economically feasible, one needs to formulate certain optimization problem. One needs to formulate certain optimization problem, and in this optimization problem, one essential component is minimization of investment and operational costs. Okay. Now, what do we mean by investment cost? Investment cost means if I want to construct a new distribution line, I need to put a lot of money to install this substation, or inside the substation, to install the power transformers, to install this different bus schemes, or to install whichever is associated to build this particular substation. Okay. So, building a substation is essentially a planning which needs certain amount of money, and this money will come from this investment of a particular financial stakeholder. Okay. Now, in order to build a whole distribution network similar to the substation construction, we need to invest money to construct the feeders, we need to invest money to construct these overhead or underground distribution lines, and we need to also invest we need money to install these distribution transformers, and from distribution transformers to the consumer's premises, whatever lines we require, that is called secondary distribution lines. Now, from substation end to the customer end, we in order to build a distribution network infrastructure, we need to construct many things which need some investment. which needs money, and these investments is called this capital investment. Okay. And apart from this capital investment, money is also required in order to run this distribution network over a period of time, and that periodic expenditure is called operational expenses or operational expenditure. So, in a typical planning process, we do optimize this investment cost and operational cost. Okay. And we have different planning models, which I am going to show you in the next lecture, in which different types of optimization problems are formulated and these are solved. Okay. So, different features are included. Based upon that, we have a very voluminous literature on power distribution system planning. Okay. So, in today's lecture, I will particularly focus on some of the financial parameters which one should know before they try to understand these different planning models. Okay. So, as I said, this any type of planning will involve this a cost function, because it is essentially a optimization problem. So, and that cost function is called as planning cost. Okay. So, it is a this cost function maps multi-dimensional parameters into the common basis. That common basis is basically the money or cost, and that is represented by either in dollar or whatever currencies we use in different countries. Okay. So, here for simplicity I will use this dollar as the currency. So, that means this planning it requires certain amount of money, and apart from this this planning and its implementation, we have many other entities. So, with that we can construct a particular distribution network, and with this multi-dimensional entities we bring all these multi-dimensional entities into a common basis, or we map them in a common basis, and that common basis is our dollar for this planning. Okay. So, we have many parameters, like we need many materials, we need many equipment, we need land of course, to install the substation, and we need to purchase this land. One needs to purchase this land, and this land purchase will have several other requirements which also need money. We need labor cost, we need government taxes, we need maintenance cost. All these things are different entities or different parameters. Okay. We bring all this to a single common basis from, and that is basically this money or the dollar or rupees for our Indian scenario. So, ultimately we need this dollar or rupees or euro, whatever you can say, in order to do all these activities, in order to do, install a distribution network in a particular area. Okay. And so, ultimately we translate all these different multi-dimensional parameters into a single basis, that is called dollar or rupees. And this planning cost can be also of two types. One is called initial investment cost, another is operational or recurring cost. Okay. So, suppose I need to build a new distribution network in a certain locality. Okay. So, what sort of cost will involve in this process? So, there are various cost, as I explained, and this cost can be categorized, this cost components can be categorized into two broad areas. One is called capital investment cost, which is a one time cost, or maybe it is a periodic cost, but ultimately it is a single time investment cost, and another is called that operational cost, which is basically function of time, and this is a recurring cost. So, this in initial investment cost is of course non recurring cost, and whatever others cost which are time varying, we can categorize as recurring cost or operational cost. Okay. So, what are these fixed costs? So, fixed costs are those which do not vary as a function of any variable element. Okay. For example, annual cost of taxes, insurance, inspections, scheduled maintenance, etc. So, these are the fixed costs we require every year, and variable cost which will vary with certain variables. For example, this loading in a typical substation, loading will vary from one year to another year, and according to this loading there are some cost components which will also vary. For example, the cost associated with the energy loss. Okay. So, if your loading varies, so as the your cost of energy loss which will also vary. Okay. So, power loss or energy loss, which is a one of the cost components of variable cost, which is one of the cost components under this recurring cost. Okay. Now, in many engineering economic evaluations, fixed cost include all cost except this variable cost, such as fuel and losses. Okay. So, whichever are variable cost, apart from those cost, all other cost will include as fixed cost. Okay. Now, next is another important thing that I am going to discuss, that is time worth of money. Okay. That which means that any utility planner must deal with two types of time versus money decisions. Okay. First one, deciding whether a present expense is justified because it cancels the need of future expense. Second decision involves determining a present expense is justified because it will reduce the future expense by some amount. So, these two I will explain with some illustrative examples, that I have. For example, I can tell you there are many decisions that we have in order to plan a network. Plan means it is planning and implementation. In order to plan and plan and construct a network. For example, I have an example later on I will show you. Suppose I build a substation. Okay. So, when you build a substation, there are several decisions that one needs to take, and one of the decisions is how many number of power transformers I will be locating in a substation. Okay. And that planning decision is basically taken based upon the future loading of the substation, that how much loading may happen or will appear in near future. Okay. And this type of planning is usually called long term planning, that I build a substation which will work for let us say 10-15 years of a period, or even more than that, 20 years or 25 years. Now, there are many possibilities that I can take a decision that I will install two power transformers of let us say some capacity 10 MVA or 20 MVA, 25 MVA each. Okay. And now, the question is, should we install two transformers at the very beginning of the construction of the substation, or I should start with a one power transformer at the initial few years, then I will add another transformer as a capacity addition of the substation. So, those type of decisions are normally taken by considering time worth of the money. okay, considering time worth of the money. Okay. So, this I have a very good example that I will show you. Okay. So, the question is actually one needs to understand that the value of money changes with time. It does not remain fixed with time. It means that suppose I have 100 rupees with me today at this moment, okay, 100 rupees or 100 dollar. Okay. Will it mean that it has the same worth after 5 years? The answer would be certainly no. Okay. So, if we have some amount of money at this present moment, that does not mean that it will have the same value, same worth after 5 years. Okay. And therefore, one needs to understand the timing on the investment, which is very important, that when should we invest, that is very important. Okay. So, this is a typical type of financial parameter, but in order to understand these different planning models, even we the electrical power system engineer, we need to understand those things. Okay. So, that is what I was talking about, some of the investment decisions that about the substation size, conductor size, these are taken based upon this future scenario, that I may construct a substation with 110 MVA power transformer, but whether that capacity would be enough after 10 years, that I need to see first. And if it is not so, then I have to either take the decision of capacity addition during that type, which would be probably the costlier option, other if we compare to if we take the decision to install 2 similar transformers right now or not. So, those analysis should be done prior to the start of the construction of a network. Okay. Now, in order to understand in a bit finer way, so let us study this present worth analysis. Okay. So, this present worth analysis is an important tool. It is an important tool. It gives you the answer of many decisions. It gives you answer of many decisions. For example, suppose I have two questions. I have two questions. Question 1 is, I have to purchase something in next year. Okay. And I know it will cost, let us say $100 in the next year. Okay. So, this is question 1, that I have to purchase something in the next year, and I know that it will cost $100 in the next year. Then the question is, should I have $100 today to purchase the item in the next year. So, this is the question, that I have to purchase an item in the next year, and I know that it will cost ₹100 in the next year. Now, should we have ₹100 today, so that I can purchase it next year? This answer would be obviously no. Answer would be obviously no. I should not require to have $100 today, so that I can purchase a item which will cost $100 in the next year. I should not have. then how much amount we should have. So, the next question is Q 2 is how much amount should I have. So, if the answer of the first question is no, that that I do not require to have $100 at this present time, at today, at this instant of time, in order to purchase an item which will cost $100 in the 1 year after that or in the next year. Okay. So, if this answer is no, then question is how much amount should I have. Okay. Should we have rupees, should we have $90, should we have $95, should we have $110 or how much. So, that answer will give you if you know this present worth analysis. This answer will give you if you know this present worth analysis. Now, what this present worth analysis is? This present worth analysis is a method of measuring and comparing costs, cost and saving that occur at different times on a consistent and equitable basis for a decision making. Because in a planning you have to understand that if I need to plan for construction or for installation of a distribution network, there are many things, there are many decisions which I need to take time to time. One example I already gave you, that what should be the rating of the power transformer. Then the next question is only one power transformer, will it be enough to supply all this load which will appear in the next 10 years or 15 years? Then I have to answer this question. So, there are many possible questions will come, okay? And in order to answer this effectively, I need to bring all these different value of money in different years ahead to a common form, and that form is basically present form, that I may have to take a decision that I need an investment one in 5th year of my planning, okay, or 7th year of my planning. Now, what would be the value of that investment in the present time? That is called this analysis is basically called present worth analysis. So, it gives the present worth of any money which we need in next 5 years or which we need next 10 years. Okay. And we have a factor called present worth factor. It represents this value of money a year from now in today's term. Okay. So, the value of money at any time in the future can be converted to the equivalent present worth. Any value of money which I require in future can be converted to is equivalent present worth, and that process of converting any future investment or any future cost required to this present value is called this present worth analysis. For example, as I said, I need to invest rupees, I need to invest this $100 from 1 year after, and then how much money should I have, so that I can purchase that item. Okay. So, in order to understand that, I have to bring this $100 that amount to the equivalent present form, that what is the present worth of that particular money, and that is basically done by this equation, that value of x dollar in t ahead of time is basically x multiplied by this p to the power t, where p is basically this present worth factor and t is basically this year in which that investment is required. Okay. So, suppose this P is basically equal to 0.1. Okay. So, I can find out that answer of this question 1. So, then answer of question 2 is that how much amount I should have, so that I can purchase an item which will cost $100 in the next year from after 1 year. Okay. So, that I can find out if I brought this $100 to this present $100 to its present worth. So, the present worth of $100, the present worth of $100 which I require to purchase an item in the next year, which I require to purchase an item in the next year, in the next year is 100 multiplied by this P is given 0.1, that is 0.1 to the power t, t is here 1 to the power 1. So, this gives you $90. So, that means, if we have $90 at this present time, then and if this present worth factor is 0.9, sorry, I am sorry. So, this present worth factor is suppose 0.9, not 0.1. Present worth factor is considered to be 0.9, then I should have this $90 with me. So, that I can spend $100. I can spend this to purchase the item which will cost $100 after 1 year. Okay. So, I need not to have $100 at this moment. If I have $90, it is sufficient. Why it is sufficient? Because this $90 if I invest somewhere which will return, assuming that it gives a return of some percent, and that return itself will make this $90 to $100. So, that I can purchase this item. Okay. So, basically that means an item which will cost $100 from a year ahead, its present worth is $90, assuming that this P is basically 0.9. Okay. P is basically 0.9, and this is the expression by which we can brought down any quantities to its present worth. For example, if instead of this $100, suppose I can say that I want to purchase an item after 2 years, and after I know that after 2 years its cost will be let us say $110. Okay. Now, what would be the present worth of this that particular item? At this present worth, it would be equal to 110 multiplied by this P to the power t, that is 0.9 to the power 2, that is 110 multiplied by 0.1. So, it will give some amount. Okay. So, if we have some amount, this amount at this moment, at this time, then I will be able to purchase an item which will cost $110 after 2 years. Okay. So, that is what one should understand, that is what I want to convey, in this particular slide. Now, the next question is how we decide this present worth factor, that how much value we should consider. This present worth factor is basically function of another parameter which is called discount factor. So, this present worth factor, it is time varying, of course, you can see. So, it is basically function of time as well as one parameter, that is called discount factor, okay, or discount rate. So, this present worth analysis discounts the value of future cost and saving versus today's cost and saving. Okay. So, this discount rate is used an analysis that is represented by this variable d, which is perceived the rate of the reduction of the value from a year to a year. Okay. So, it gives the basically the value of this present worth factor p. Okay. And what is that relationship? This is what the relationship is. It is equal to 1 upon 1 plus d to the power t. Okay. 1 upon d to the power t. So, this is basically p to the power t itself, there is an error. So, basically this p t is basically equal to 1 plus 1 upon d, one needs to understand. Okay. And p t is p to the power t will be equal to something like that, where d is basically discount rate, d is basically discount rate. So, if we know this discount rate, I can find out what should be the present worth factor, and if I know this present worth factor, I can compute that what should be the value of a money which I need let's say at tth year. Okay. Now, next question is how do we determine this present worth factor and this discount rate. So, as I you can see the first bullet point, there is no uniform rule or set of guidelines available. So, that one can say that this is how we can decide that this would be the discount rate, and once you know the discount rate you can find out the present worth. Okay. Now, how it is then determined? It is basically determined by this by any particular company's financial planners. Okay. And this discount rate is fixed by the utilities financial planners based upon various interest rates, for example, this prime rates for mortgage, etc. So, there is a financial planner in a particular company which will basically decide that what should be the discount rate for a particular planning. Okay. And once you get that discount rate, if it is 10% or 12% or whatever it is, based upon that you can find out this present worth factor, and based upon this present worth factor you can bring down the present worth of money of any future investment which is required. Okay. Now, basically this discount rate also involves, this determination of discount rate also involves certain amount of risk. Okay. And a low amount of risk means a relatively low interest rate or discount rate and vice versa. So, determination of discount rate involves certain amount of risk. Okay. Also, there is another financial parameter that everybody we know, that is called inflation. Okay. So, inflation is basically responsible to raise the cost of everything involved in any type of planning. Okay. So, we know that this prices of any equipment or any device will change from year to year, and that change is basically due to this inflation. So, we know that government calculates one inflation rate at a given time. Okay. So, but many times this inflation is not included into this computation of present worth factor, and sometimes this inflation is also included. Now, if this inflation is included, then it is called inflation adjusted present worth factor, and sometimes inflation is not included because it is assumed that inflation will affect all these stakeholders in a uniform rate. So, if there is inflation of 3%, it means that equipment will cost 3% more, labor cost will be 3% more, or whatever is associated with this planning will cost 3% more. So, if there is a uniform change of this pricing, then it will not influence in the relative cost of the overall planning. Okay. And in many this distribution system planning model, this inflation rate is embedded into this computation of discount rate. So, that means discount rate is computed in such a way that it is it considers certain amount of inflation into this account. Okay. So, this is how we need to understand about this inflation and discount rate. So, sometimes this present growth factor in some of the planning model, which I will show you later on, they embed this inflation rate into this present growth factor, and they call it as inflation adjusted present growth factor. Okay. Now, I am going to another important financial analysis, which is called levelized analysis or levelized cost analysis, which is used to apply this time value of money to initial and future cost to develop an equivalent constant annual cost. I will show you an example. Suppose this is what this it is a planning of a particular it is a planning cost of a particular building a certain infrastructure in a power system. So, it is a time varying planning, costs. Now, here you can see that this total planning period is total planning period is equal to 34 years, and you can see the year to year this cost is varying. So, the cost is highest at this 4th year, cost is it is lowest at 5th years, then slowly this cost is increasing and it is somewhere higher in 16th year, then again it is reducing and so on. So, these are basically time varying cost. So, these are time varying cost, time varying planning cost. Okay. Now, looking at this particular planning, it is very difficult to understand that how much annual cost is required, so that we cope up with this planning. Okay. And most importantly, if I want to compare this planning with another planning which is having another set of time varying cost, okay, how do we compare these two planning alternatives? So, in order to bring them in a same platform, we use this levelized cost. This levelized cost will convert these time varying cost components in different future years to a constant cost. So, this is basically this levelized cost, constant annual cost, by using which we can compare one planning alternative to another planning alternative. Okay. Now, how it is done? So, basically this levelized cost is useful, as I said, to compare different project or plans. So, I have to construct suppose a distribution network, and I received let us say 3 to 4 planning alternatives, and I need to compare this planning. Now, how do we compare? Because all these planning costs are time varying. So, one thing that I can do, I can bring all these future costs with this present growth cost and I can compare them, and also I can convert this present growth cost into a fixed annual cost, and then also I can compare. Okay. So, this levelized cost is basically the second one, in which this present growth cost is converted to a constant annual cost, and by doing so we can compare different alternative plans, different projects. Okay. Even if their actual cost changes greatly from one year to another year. Okay. So, basically this levelized cost involves finding a constant annual cost whose present growth equals to the total present growth of the plan. Okay. And levelized cost analysis is a particularly useful in comparing different alternative plans to arrive at that which plan one should take for this implementation. Okay. Now, how do we determine this levelized value or levelized cost? So, this is the expression through which we can derive this levelized cost, where you know that capital Q is basically this present worth of a particular planning or time varying planning, and small d, as you know, it is discount rate, and t is the years, okay, for the planning. Okay. Here you know t is not given, basically instead of that n is given. So, n represents the number of years. So, if your n is equal to 20, that means it is a plan for 20 years. Okay. Or planning horizon is equal to 20 years. Okay. Now, I have two examples to illustrate how to determine this levelized cost. Okay. Now, the first example is building a substation, building a new substation. I have two alternatives. One is alternative A, which means that in this alternative I will take the decision that I will install 225 MVA transformers at a particular time. Okay. So, the idea is that I need to compare two planning alternatives. In one alternative, I will consider that I will install 225 MVA transformers at a time. Okay. And in alternative B, we will defer the second transformer installation by 4 years. Okay. And we will install it from year 3 to year 7, So, that is the two alternatives we have or two possible planning alternatives that we have. In one alternative, I will take the decision that I will install 225 MVA transformers at a time. Another planning alternative is that I will defer one transformer installation by certain period of time, that is 4 years. Okay. And this table gives your total 8 years of this comparison. Okay. I will take it from this Lee Will's book. It gives a very good insight that particularly to understand this importance of present truth analysis, particularly to understand the importance of levelized cost analysis. Okay. Now, what this table is showing to you? This first column is basically year of planning. So, 0th year we will start construction of this particular substation, we will do this planning, etc. Then first year we will basically start, because at 0th year one needs to frame out this planning, and then one needs to initiate this land purchase, etc., etc. And in the first year we will start this construction. Okay. Now, this part is showing you, the result means alternative A, where I means we take the decision of building 2 transformers at a time. Okay. And this part is basically providing you this planning cost for alternative B, where we will defer the investment of one transformer to certain years. Okay. Now, in the first year you can see we need these are the cost components. We have 3 cost component. One is capital investment cost, another is O, M and T, that is operation and maintenance cost. So, this O, M and T is operation and maintenance cost. And this one is basically third column is representing the cost of energy losses. So, losses stands for the cost of energy Okay. Similarly, here also in alternative B we have this capital investment cost, operational maintenance cost and cost of energy losses. Okay. So, we need same amount of capital investment cost in the first year in the both alternative plans, that is $20 each, and you can understand that this is not $20, this is 20 multiplied by $1000. So, this is basically all are equal to 20 multiplied by $1000. So, that much we require as the capital investment cost, or $20,000 we require for as a capital investment cost in both the planning alternatives in the first year. In the second year, in alternative A we require 370 multiplied by 1000 or 370,000 of $370,000 as capital investment cost, whereas in alternative B we require only 290,000 of capital investment cost. Okay. Now, why we require less amount of capital investment cost in alternative B? Because in alternative B we took the decision that at that time at this second year or up to third year we will only install one transformer. So, it accounts for installation of only one transformer and associated equipment. So, its cost will be obviously lower as compared to this alternative A, where we took the decision of installation of two transformers at a time. Okay. So, in the third year you can see in alternative A all the two transformers are installed and it is it requires that much of capital investment, whereas in alternative B we have installed only one transformer. So, its cost will be less. Okay. So, its cost will be at least 40% or 30% less. Okay. Now, so after this first, second and third year we have installed both the transformer in alternative A. So, there is no capital investment cost required after that. Okay. So, total capital investment cost is $1,400,000. Okay. And after installation of this two transformer, these are this operation maintenance cost and these are the operation maintenance cost and these are the cost of the losses, cost of the energy losses. Okay. Which are also time varying depending upon that how much loading they are having. So, this loading this column shows you this loading. Okay. This column shows you this loading and accordingly this cost of energy losses will also vary. Similarly, in alternative B we have these are these operation and maintenance cost of one power transformer and these are the cost of energy losses for one transformer. Okay. Now, you can see up to this fifth year when my load demand is 18.5 megawatt, this alternative A which install 225 MVA transformer. So, it does not have any problem, but this alternative B it has installed 125 MVA transformer. So, if further load grows it needs to install another transformer in order to cope up with this additional load. So, that is why this additional in the sixth year it decides to install another transformer which requires another capital investment cost of $80,000 and at seventh year $560,000. Okay. So, this accounts for installation of the second transformer. So, this accounts for installation of second transformer. Okay. And accordingly this operation and maintenance cost and cost of energy losses will vary. Now, if you compare this cost of energy losses in third year of this alternative B and alternative A, you can see the cost of energy losses is higher in alternative A in third year as well as fourth year, fifth year and sixth year as and up to this fifth year, because only here in this alternative A we have two transformers already we have installed, and the loading is not much. So, they have to share this load. So, if loading is 12 megawatt, so each of the transformer will share half of this loading, and many times this due to light load condition there will be this transformer will be very much lightly loaded, which accounts for a higher amount of no load losses, which makes the total cost of energy losses higher as compared to alternative V, where we have only one transformer whose loading is obviously much higher, which whose loading is double than this alternative A. Okay. Now, if you add up all this capital investment cost, operation maintenance cost and this cost of energy losses for alternative A, then you will get it is 2492 multiplied by $1000. Okay. So, that is the total cost we require. We did not consider any sort of present worth analysis at this time. Okay. Now, we do the same thing for by adding up this capital investment cost, operation maintenance cost and cost of energy losses for alternative B. If you sum up all these three, then this will make the total of 2534 multiplied by 10 to the power 3 dollar. Okay. So, this is basically total this multiplied by 10 to the power 3 dollar, and this is also this much multiplied by 10 to the power 3 dollar. Okay. Now, if you compare of this total planning cost and this total planning cost, so apparently you can see that this alternative B is much costlier in view of this particular total cost that we require. Okay. But does it mean that this alternative B is really costlier? This you can understand with the present worth analysis. So, here if you simply add up the individual cost which occurs in different time. Okay. So, this will not actually represent this total cost, okay, because this $52,000 or this $110,000 this occur in different times. They do not occur in the same time. So, if you simply arithmetically add these two cost components which occurs at different times in a year, then this will not be this will not reflect the actual cost. Okay. So, in order to have this actual cost analysis, we will consider this present worth analysis. Okay. So, here we consider this discount factor as 0.9. So, present worth factor will be 0.9 at year 1, and at year 2 it will be 0.9 to the it should be 0.9 square. So, this will give you 0.81, and year 3 it will be 0.9 cube, it will give you that much. In year 4 it will be 0.9 to the power 4. So, this will be this and similar, so on and so forth. So, this at year 7 this will be 0.9 to the power 7, this will give you 0.48. Okay. So, these are the present worth factor which converts this future value of money to the present value. Okay. So, we need to multiply this present worth factor to all the cost component in order to bring them to the present worth or to the present value of the money. Oh, okay. And what we did, we multiply 0.9 with this 20 and this 20 as well. So, what we will get? We will get 18. So, this is not 18, but this is 18 multiplied by 10 to the power 3. So, this is basically $18,000. Similarly, we multiply at year 2, we multiply 0.81 with the all cost component which occurs at second year, that is 370 and 290. So, if you multiply 370 with 0.81, it will give you 300. So, as this 235. Okay. So, this shows you the present worth of this capital investment cost, which is actually 370, but this 300 is basically representing this present worth value of this capital investment, which is actually $370,000 at after second year, okay, after year 2. So, all these cost components are multiplied with their corresponding present worth factor, and they brought down to the present worth. Okay. So, what we will get? This we get this total capital investment we require is 1054 multiplied by 10 to the power 3, and that we get by adding up this all these 3 capital cost investments that we require in year 1, year 2 and year 3. Similarly, we add all this operation and maintenance cost. These are present worth cost only. You can verify actual cost was 52. If you multiply 52 with this present worth factor, that is 0.7, it becomes 38. Okay. It is actually 38,000, but here we have shown as 38. So, if you add up all these cost components, in fact, you can verify here. Here you can see operation and maintenance costs are same over different years, year 4 to year 5, year 6 and year 7. But when you multiply it with different present worth factor, they are become different. They become 72, 65, 58 and 53. So, because you have different present worth values, present worth factor values. Okay. Now, after adding up this will give you $286,000 for operation and maintenance cost, and $343,000 for cost of energy losses. Okay. And finally, if you sum up all these 3, this will give you total present worth cost of this alternative plan, that is 1683 multiplied by 10 to the power 3 $. Okay. Similarly, if you multiply this capital investment cost, this capital investment cost of course is the present worth cost. We got them from by multiplying this corresponding present worth factor from the actual cost. For example, you can see here for alternative B at 6th year, this we need capital investment cost as $80,000, whereas when you multiply it present worth factor of 0.53. So, this become 43, okay, $43,000. Okay. So, if you add up all these things, this will give you 1068 multiplied by 10 to the power 3. Similarly, if you add up all this thing, you give 243. If you add up all this cost of energy losses, you get 321. Then you add up all these 3 in order to get this total planning present worth planning cost, which is 1632 10 to the power 3 $. Okay. Now, you can see if you arithmetically sum up all this planning cost, it is $2,492,000 for this alternative A. Whereas, if you sum up them with this present worth factor, and this represent this present worth of this time varying investment decision, then this value will come down to be $1,683,000. Okay. Similarly, here also $1,632,000. Now, you compare these two plan, or alternatively we can say the present worth value of these two alternative plans. One is $1,683,000, another is $1,632,000. If you compare these two, then obviously you can see this alternative B, it will be cheaper, this will be cheaper, this will be cheaper as compared to this alternative A. Whereas, if you simply add up, arithmetically add up and compare, then this will be costlier, this will be costlier. Okay. So, that is what the contradiction is. If you do not add this with present worth factor, you whatever this actual cost you are getting, that will not reflect the actual cost, okay, and that one needs to understand. Okay. Now, from this present worth cost, we can eventually plot this alternative A and alternative B. So, in that plot you can see we have some portion of capital investment, we have some portion of operation and maintenance, we have some cost of energy losses. So, this gives a glimpse of idea that which of the cost components will influence and how. Okay. So, you can see in alternative A, this 4th year, this is basically year wise cost, total cost year wise, these are basically year wise cost comparison, and you can see that in alternative A at 4th year we have highest amount of dollar required or maximum value of the dollar required, and so as this alternative B, but we have also need in 7th and 8th years higher value of this dollar. Okay. And because we install, why it is high compared to these two, because here we take the decision to install another transformer which accounts for considerable amount of capital investment cost. Okay. Considerable amount of capital investment cost. Okay. All right. Whereas, you know, here present load cost is around 500, here present load cost is much higher than that. Okay. So, these two are different scales that one need to notice, although they look like same thing, but this is up to 550, here it is around 800. Okay. Now, from this present load cost, we find out this levelized cost. How to find out? These are the two steps. First, you find out this present load cost, and then you by using this equation of this levelized cost, you convert it to this levelized cost. So, what we have done here? So, in alternative A, as we have seen, the total present load cost is that much 1683000, that much of present load cost, and if you convert it to this levelized value, this will give you that much, that is around $358,000. Okay. By using the same type of analysis in alternative B, you will get this present load, this levelized cost as around $347,000. So, if you compare this and this, you will get around $10,000 difference of the annual levelized cost, which is very important. Okay. So, here you can understand that alternative B accounts for $10,000 less amount of levelized cost as compared to alternative A, which is basically significant amount, and this helps you to choose a which option should be economically more suitable. Okay. I have another example, short example, also I took from this Lee Will's book. I sincerely acknowledge for that, where I want to install this lighting of a particular area, and I have three possible options. One is to have purchase an incandescent lamp, another is to purchase a halogen lamp, another option is to purchase a fluorescent lamp, and all the options will give you same amount of light in lumens. Okay. Now, incandescent lamp, its lifetime is 3 years. So, its lifetime is equal to 3 years, because different lamps, you know, their lifetimes are different. Then halogen lamp, this lifetime is equal to 5 years, and for this fluorescent lamp, lifetime is equal to 6 years. So, they have different lifetimes, and so as they are different purchase cost or different cost required to purchase. So, here you can see for purchasing incandescent lamp, we need only $2 as capital cost. Okay. But it will account for this energy cost, that means how much energy it will consume. If you convert it to the energy cost, this will account for energy cost of $23 in each year, each 3 year. Okay. This is basically a variable cost, or recurring cost, and this is what the capital investment or one time cost. Okay. So, if you add up these two, so total cost will be $25 in the first year and second year onwards $23. Okay. Now, if you convert this cost to the present worth factor by considering this present worth factor is 0.9. So, you get their corresponding present worth dollar. Okay. And if you sum up all this present worth dollar, it will give you total present worth is around $57.9. Now, with this present worth, if you determine this levelized cost, so you get this levelized cost for around $23 per year in a span of 3 years. Okay. After that, we need replacement. Similarly, for halogen lamp also we need capital investment cost is $8. So, as the energy cost is lower than this incandescent lamp, and in similar way you determine this present worth cost, and if you sum up this total present worth cost. So, total present worth cost will give you around $55. This is for span of 5 years and levelized cost will be around $15 per year. So, if you compare this levelized cost and that levelized cost, you can see almost $10 saving that you can get with this halogen lamp, whose capital investment cost is 4 times higher. It is actually 4 times of this incandescent lamp. So, just by looking at this capital cost, you cannot decide that actual cost it will incur in future years. Okay. So, you have to do this present worth analysis as well as you have to do this levelized cost analysis. Now, in the third type, that is fluorescent lamp, this capital cost is much higher. You can see as compared to this halogen or incandescent lamp, it is much higher, but energy cost is significantly lower, and so as the total present worth cost, which is around $49. Okay, and that is also for a span of 6 years. That is something that one should notice, that is also for a span of 6 years. So, when we convert this present worth to the levelized cost, so you will get it is around $11 per year, $11.6 per year, which is of course significantly lower than this incandescent lamp and also lower than the halogen lamp. So, the main essence of the fact that I am trying to explain is that not only this capital cost, looking at this capital cost, one cannot take the decision that what particular decision, what alternative decisions we should select. In order to do so, we need to find out this present worth analysis and finally, this levelized cost analysis. Okay. So, these are the important things to initiate the understanding of power distribution system planning, and with this I will finish this part of the lecture, and I sincerely acknowledge this book H. Lee Will's book of power distribution planning reference book. Okay. To have the idea, if one needs to have more understanding and different financial parameters, you can go through this book. Okay. Thank you.